In this video, we're going to be talking about piecewise functions, and we're going to start off by defining what they are. So a piecewise function is a function built from pieces of different functions over different intervals. So I have a graphic here to help explain that topic. So see how we have three different functions, number 1, number 2, and number 3. If we imagine cutting off a piece of each of these, so in this case, we're cutting off just looking at this piece of this linear function. We're just looking at this piece of the constant function, and then just this piece of the quadratic function. If we took each of those pieces, it looks like this, and took those cuts, and then piece them all together, this would be considered a piecewise function. For each specified domain, or the x values, we're using different functions. So let's try to write this equation. Let's call it maybe f of x. With a piecewise function, there's a big curly brace, and it's going to list each of your functions. So we had 3 here, so I need to list all 3. The first one was just x plus 2. The second one was just y equals 1, so I'm just going to write 1. And the last one was y equals x squared, so I'm going to write x squared. So it's these 3 functions. But the important piece, pun intended, is to remember which x values we're looking at, or which interval, because see how we have this entire linear function. So which piece am I talking about? Am I talking about this piece? Am I talking about this piece? Am I talking about this piece? I have to let you know which piece I'm talking about, and I do that by using the x values. So in this case, we use the linear function when x was less than -1. This is where -1 is, x equals -1. So it's where x is less than -1. It's difficult to tell based on this example, but I am going to make note of something in a second. Notice that's just a little comma beside the actual function, and then after that you have to put which interval are we using. So for number 2, we used from -1 to +1. So when you have an interval with a least value and a greatest value, I would start with the least value and do my inequalities and get to the greatest value. So this is essentially saying we use 1, or the number 2, when x is in between -1 and 1. And for the last one, x squared, we're going to use the quadratic after 1. So when x is greater than 1. So notice too, like the definition of a function is that you can't have the same x value give you 2 different y values. So we couldn't have them overlap. That means there only can be, at x equals -1, there should only be 1 or equal to. There can't be 2 or equal to's at -1 for the x values there. Same thing with the +1, right? So we can only have the or equal to at one spot. It can't be at both spots. So the next thing says, is just a note about continuity. So I'm actually going to draw this before I'm moving further. When this is less than, right? This is less than or equal to. This, and then this is greater than, and then greater than or equal to. So these, the value is not included, right? And for these, with the or equal to, the value is included. So the way that I would graph that for this blue function here is actually going to be an open circle for the blue function, because it's not or equal to, it's not included. For the red function though, notice that it's going to be included on both sides, so that's a closed circle on both sides. And then for the green function, it's not included, and so it's going to be an open circle. But there isn't just open circles. There's not because the other function fills them in. So this is a continuous function. So what's a continuous function? It has no point breaks or jumps in the graph. So a jump would be like if you like had a graph was like this, right? This is a jump because see, to get from here all the way up here, I have to jump. A point break sometimes occurs when it looks like this. So maybe I have a function, then there's just an open circle there. So this isn't like necessarily a jump like the second graph that I drew, but there is a discontinuity. So to determine whether or not a function is continuous, if you trace it without picking up your pencil, then it's continuous. If you have to pick up your pencil, then it is not continuous. So for example, this one is continuous because I can trace the whole thing without picking up my pencil. There wasn't like an open circle or there wasn't a jump. It's a continuous function. So let's look at some examples of piecewise functions and finding the key features of them. Now, if you have a pen and you're taking notes, I would suggest maybe wait until I finish graphing to write this, because the way that I'm going to do it is I'm going to graph the entire function and then cut it off for the specific interval. So I'm going to start with this linear function. So I know the y-intercept is 2, and it's linear, so it's up 1 over 1. It's also down 1 over 1. So this is my linear function, right? But I only want this function when x is less than -2. Well, x is less than -2 is right here. So I'm going to have to cut off this function on this side. Just needs to be less than. And because it's less than, notice this has to be an open circle. That point is not included. So now let's look at the next piece. X squared. X squared is a quadratic. Looks like this. But we just want this to be from -1 to 2. So I'm going to have to cut it off. -1 is right here. 2 is right here. So that means I'm cutting off this piece and also up here. So it's going to stop there. Because there are or equal to signs on either part, this one is a closed circle. Whoops, let me try that again. This one is a closed circle, and this one is also a closed circle. I'm going to erase my the black dotted lines in just a second. They're just helping me look at the correct domain. Domain is the second piece of our piecewise function. The pieces, I shouldn't say piece. It's the second part of each piece. And then the last one is just 3. So if it's just a number, that's a constant function. So that's just like a horizontal line at y equals 3. So looks like this. But I'm only looking for when x is greater than 2. So x is 2 right here. What I'll need to do is erase all of that. And then it ends up being, kind of erase my quadratic a little there. This is an open circle because it's not included. And this continues forever. Okay, so now I have my piecewise function, and I am going to take away these black lines so that I don't get confused by them. But there are 3 different pieces to this piecewise function. A linear part, a quadratic part, and a constant part. Now what I want to do is determine a few things about this. And I'm actually going to start by figuring out when is the function increasing and when is it decreasing. So I'm going to start by saying the increasing portion. When is the function increasing? So it's increasing whenever I trace the graph and it's going up. So if I start over here, as I'm tracing left to right, it is going up. So it's increasing from -infinity until we get to -2. Notice at -2 it's an open circle. We're not including that endpoint. It's also increasing from here to here. because as I trace going left to right, it's going up. So I'm going to put a little union. And then from 0 to +2. Remember, we define our increasing intervals by the x-axis. The decreasing intervals are when I trace this graph from left to right, it's going down. So as I trace, the only piece that's going down is this one. So the decreasing interval would have been from -1 to 0. Don't forget to define this on your x-axis here. Okay, so from -1 to 0, it's decreasing. There's actually a part that is not increasing, nor is it decreasing, and that's this piece. That's the constant piece, because it's not going up, it's not going down, so we wouldn't include that in increasing or decreasing. So the next thing that we need to find is the x-intercept. Does this have an x-intercept? Remember, it's an x-intercept if it crosses the x-axis. In this case, there's only one x-intercept, and that's right here. The reason this point is not considered an x-intercept is because it's not actually a point. It's an open circle, not a closed one. So the x-intercept, the only x-intercept is 0, 0. Because that is the origin, that is a special point. That's also the y-intercept. It's where it crosses both the x and the y axis. And so the y-intercept is also that point 0, 0. Now, if we look for a maximum, there is an absolute maximum here. So an absolute maximum, and it occurs here at 2, 4. Absolute max at the point 2, 4. There's not an absolute minimum because if you notice, this function is going to go down forever on this side. So there's not an absolute minimum, but there is a relative minimum or a local minimum at this turning point of 0, 0. The next piece asked us to evaluate h of 2. So just a couple things about function notation if we've forgotten. So this is called h of 2. This is the input. Remember, the input is your x value. We want to find the output. The output is the y value. So they're telling us x is equal to 2 and wanting to know what's y. So we could do this two ways. I'm going to first do it by the graph and then show you how to do it by the equation. On the graph, h of 2 means I go over right 2. If I go right 2, okay, so I have this point and I have this guy. The point that's actually is the closed circle. So if you have two things over top of each other, one has to be an open circle, one has to be a closed circle. It's actually the point at the closed circle. So this is going to be 4. The other way to do this problem is to use the equation. So if we wanted to find h of 4, what we would need to do, or h of 2, excuse me, what we would need to do is find out where does 2 fit? Which piece does 2 fit in? Well, is 2 less than -2? No. So it cannot be the first piece. Is 2, in between -1 and 2? Well, it is 2, and so because of the or equal to sign that's here, it's going to be my second piece. So that means I just plug it in for x, which gives me 4. Either way. The next piece asks us about our domain. Remember that domain is the set of all x values. So if you notice, this one starts all the way over to the left. So we're at -infinity, and it goes until we get to this point. -2 is not defined on this graph. So I'm going to use a parentheses, not an open circle, or because it's an open circle, not a bracket. Now the next domain, we have some pieces missing from our domain here. Nothing in between -1 and -2 exists on this function. But we do have a value picking back up at -1. So -1, and then we're good until we get to 2. Now, see that there is a point at 2, so we're good there, and then it picks it back up right after 2 for forever. So our domain is going to be from -infinity to -2, and then picking it back up at -1 all the way to infinity. Our range is our y values, and so we're looking this time up and down. So we already talked about the fact that this goes down forever, so -infinity. we have to make sure that every point in between is accounted for. So over here, 0 is accounted for, right? And then we have the range going up, 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 up. This is accounted for, this accounted for. This is the highest our function goes, and it goes all the way from every point in between the lowest point and this point is accounted for, at least at some point on the graph. So we would say our range is from negative infinity to 4. 4 is the highest point. Now some of you may be thinking, but what about this? This is 3. Well, 3 is already in this interval, so we don't have to include it twice. The last thing is this continuous? The correct answer is no. This is not continuous, because in order to graph this, I would have to pick up my pencil here and then again here. So this is not a continuous function. Let's look at example number 2. We are going to look at how to graph in Desmos in a second, but example number 2, they already gave me the graph, and so I'm just going to look at this graph. I don't have to graph it this time, and determine these key features. So where is the function increasing? So I'm going to start by tracing and decreasing. I'm going to start by the left, going all the way to the left and tracing. See how this piece right here is decreasing. So it's decreasing. That's right, I and D. It's decreasing from negative infinity until we get to this point right here at negative 2. Now, from here to here, it's increasing. So from negative 2 to negative 1, remember we're looking at our x-axis, we are increasing. And then from negative 1 to the rest of the function, which it goes on forever because of that arrow, it is decreasing again. So I would say negative 1 to infinity, it is decreasing. Remember, when I say infinity, I know this is going down, but when we name our intervals, increasing and decreasing intervals, we're talking about the x-axis. So although it's going down, it's also going right. So right is positive infinity. For our x-intercept, where it crosses the x-axis, we would say there are none, because it does not cross the x-axis. For our y-intercept, it crosses the y-intercept or the y-axis at 0, negative 3. There is no absolute maximum, and there's also no relative maximum. So we would say none. There is no absolute minimum because it goes down forever. There is a relative minimum, though, where it changes direction. So this is a relative minimum or a local minimum at the point negative 2, 1. The next thing we were asked to do is find g of 2. Recall that g of 2 means that my input is 2, my input is my x value. So at x equals 2, if I go over 2, where is my function? Well, I have to go down 1, 2, 3, 4, 5, 6, 7. So g of 2 is 7. The domain is the set of all x values, so I start looking at the left-hand side of the function. Look how there's an arrow on the left-hand side. So that means our domain is from negative infinity. We're good, we're good, we're good. All x's are taken care of. There's a closed circle here and an open circle here, which is exactly what we want, but this point is still taken care of. And then we go all the way right forever. So the domain is from negative infinity to positive infinity. The range is going to be our y values. Notice this goes up forever, right? And it also goes down forever. But be careful, because every value in between is not accounted for. So we are going to start with negative infinity because it does go down forever. But notice how the highest point that it goes here is from negative 1, and then there's a jump up here to positive 1. So there's no point where y is 0. There's no point where y is like 1 or 0.5 or something, or negative 0.5. There is a gap in the range from negative 1 to 1. And so we would say from negative 1, the range exists from negative 1 to, or negative infinity to negative 1. Negative 1 is not included because it's an open circle. I'm going to say union. Now positive 1 is included because there's a closed circle there. And then it goes up forever all the way to infinity. Is this a continuous function? The answer would be no. And the reason is because I could not trace the whole thing without picking up my pencil, there is a jump from here to here. There's a jump, and so it is not continuous.